My name is Maurice Filo, and today I would like to show you a MATLAB application that I made recently that helps us build, design, and analyze or simulate biomolecular controllers using the standard chemical reaction network framework. So without any further ado, let's go ahead and just run the app by just clicking on bmc.mlapp. And when you do that, you're gonna run or you're gonna launch the app designer, which is gonna show you the design view of the application. We're not interested in that for now, so this is useful only if you want to change things and you want to access the code and the graphical user interface underlying the application. We don't want to do that, we just want to run it. So let's just go ahead and click on the run icon. Okay, once you do that, the application will run. And this is how it looks like. So let me just give you a brief introduction on what the various parts of this graphical user interface is all about. So first of all, the closed loop network is divided into a plant or the network to be regulated and the controller network. And they are here shown as a table for the plant, another table for the controller, where in each table you have a reactants column and a products column and the propensity. So each reaction is embedded in a row or encrypted in one row of the table with the reactants and the products and the propensity. And this here shows you the list of plant species. So this example is the simplest example where there's not even a controller, it's just a plant running in open loop. And we have a network diagram for that. So this is what the table is encoding for, basically. You just have two species, X1 and X2, and it can be thought of as a simple gene expression network that is not being regulated. Okay, so this is encrypted in these tables here, and the output of interest that we want to measure or basically display in the simulation is X2. Okay, and the controller is, well, there's no controller for this example. And here there's a drop-down menu that allows you to select among different networks that you have. So this network that we have now is just the open loop gene expression network, and there's nothing else. So here, this allows you to add existing networks. So if you have other networks, you're going to see that in a few minutes. You can just add them here to the drop-down menu by clicking on this button. But if you want to create a new network, you just have to click on this one here, and that's going to take you to another graphical user interface, which we're going to do in a few seconds, that will allow you to build a new network from scratch. So this here is the control panel, and this here is the plant panel. These have the knobs for the various parameters. So in this example, there's no controller, but you have only 4 plant parameters. So these are the parameters, K1, K, gamma 1, gamma 2. These are knobs that allow you to tune the various parameters and to do simulations. You can basically tune them by just, dragging this knob here. And if you want to go higher than the ranges or lower than the ranges that are shown here in the tuning knob, you can just enter it here. So if you want to increase it to 1, you just enter 1 here and enter, and that's going to increase the range to 1 so that you can tune it even further. And if you have, in case you have more than 4 parameters, you can use these different panels. So the other parameters will appear in these different panels here. But in this case, there are only 4 plant parameters. Here, it shows you the panel for deterministic simulations. And this is going to show you only the output. So in this case, the output, as I mentioned, is just X2. So this is going to show the response as in the output, which is X2. So if you just hit run, then you can just see a simulation basically. This panel here is for the stochastic simulation, and it allows you to use the parallel computing toolbox if you do check this checkbox, and it allows you to change the number of trajectories. So if you want to simulate 10 or even more, so like 100 or 1,000, if you enter 1,000 here, it will increase the range and you can select it with a slider. This here shows you the simulation time, the overall simulation time, so it's 100. We'll get back to this in a minute, but first let's go ahead and to build a new network from scratch. So what we're gonna do is click on this create new network. So like I said, when you do that, this is gonna take you to a new user interface, which allows you to load a network. So if you have another already network that is created, you can load it and then edit it, so it would be easier. But for this example, I'm just going to start from scratch. And as an example, we're going to go ahead and build the following. Let me show it here. We're going to build the following network. So let me just put it side by side so that we can do it in an easier way. Let me take this out. Okay. So in this case here, we have that same open loop plant that I mentioned previously. So you can think of it as gene expression, but we're controlling it here with a proportional integral antistatic controller, where you have the controller has two species, Z1 and Z2, and so Z2 can sense the output X2 through this reaction. It's a catalytic reaction at rate theta, and Z1 actuates the plant, or the input of the plant, which is X1, in two ways. First, it produces X1, so the rate is KZ1 of production, but it also inhibits X1, and for this example, the inhibition is a degradation inhibition. So basically X2 degrades X1 actively. And this is here shows in red shows the degradation action, delta X2 multiplied by this Hill function. So the overall input, you can think of it as KZ1 minus delta X2 multiplied by this Hill function. Okay, so Z1 and Z2 sequester each other to achieve the antithetic integral motif, and Z1 is catalytically or is constitutively produced at a rate mu. And here you can also include the dilution rates, which I'm denoting here by gamma C. Okay, so let's see. So we want to build this closed loop network. First of all, you need to specify the number of plant species. We have two, so we can just specify two. And then you can go ahead and add them. Once you press this add plant species, it asks you to enter plant species 1, let's call it X_1. And then hit next. Then asks you for the second species, you enter X_2, hit next, no more species, only 2 species, and then we can close it. Then it automatically shows you a list here of the plant species, and from which you can pick what is the output species of interest. So let's keep it X2. The second step is to specify what the number of controller species is. So in this case it's 2, so you're just going to leave it 2. You go ahead and add the controller species, same way as we added the plant species. So we have Z1_1 and Z_2. Then we hit close, we get the list of controller species Z1 and Z2. Okay, so next step is to specify how many plant reactions and how many plant parameters in the network. Okay, so the boundary, let me just say that the boundary between the plant and the controller is something that you define. I'm defining it here like that, but there's nothing that will the app can you can specify freely what the boundary is. So which is the what reaction is labeled a plant reaction or a controller reaction? That's just up to you. The app can handle whatever choice you decide to take into consideration. So in this case, I'm just going to consider 3 plant reactions. So 3 here with 3 parameters. So let's go ahead and add those plant reactions. So you click on the add plant reactions button and shows you this user interface here. So let's see. So the first reaction, let's say X1 is catalytically producing X2. So the way you do it is you select X1 in the list of species and then hit add reactant. And since it's catalytic, it has to appear at the product as well. So you hit add product, so it'll appear here. But then X2 is produced, so you can select X2 and add the product. And that's it. In case there's a coefficient for X1, you can just, use this knob to pick a higher coefficient, but that's not typically the case in biology. Maybe up to 2 it's the highest that you can think of. Well, practically makes sense. But the app allows you to choose whatever you like. So we can hit next. Second reaction is, it's just the degradation of X1. So X1 goes to 0. And the third reaction is X2 goes to 0. You hit next, no more reactions, and then we hit close. Once you do that, you get this table being updated with all the reactants and the products of each species and each reaction. Okay, so now we want to add the plant parameters. So in this case, there are only 3. There's K1, and there's gamma underscore 1, and gamma underscore 2. Hit next, no more parameters. We hit close. These parameters will appear here as a list of plant parameters. And finally, you edit the plant propensities. So this allows you to use any type of propensities, hill type functions, or just mass action or whatever. You can just, because you're just hard coding really the all propensities that you want to use. So in this case, if it's we're just going to use K1 multiplied by X1, that's just mass action. The degradation propensity is gamma 1 times X1, and observe that I'm using the same notation for the concentration of the species as the list, or as the name of the species that is listed here. Same thing goes for X2 degradation. So like this, hit next, we're done, and the plant now is fully specified. Now we're left with the controller reactions. So one can count them, and you'll see that there are 7 more reactions that I'm labeling as controller reactions. And we have 7 parameters for those. You can count those. Okay. And then we can go ahead and continue. We can add the controller reactions. So there's first the constitutive production of Z1. And there's the sensing reaction where X2 catalytically produces Z2. And there's the sequestration reaction that is the critical component of the antithetic integral motif. And there's the actuation reaction where, Z1 and X2 both, in this case, can produce the input species of the plant. So I'm just going to code it like 0 goes to X1 and then play around with the rate itself. Okay, so and there's 2 more reactions for the non-ideal case where we are allowing the controller species to dilute. Of course, this will make us lose the perfect integrator property, but let's just keep it now for completeness. So you can go and look at the reactions again. So there's 0 goes to Z1, X2 goes to X2 plus Z2, the sequestration reaction, and then there's the actuation reaction. Okay, so yeah, we forgot the negative actuation reaction, right? So the actuation reaction, there's two actuation reactions. There's production of X1 and the degradation of X1. So let me just put it here. So clear reactants, clear products. X1 goes to 0. And yeah, and then we're just left with the degradation of Z1 and the degradation of Z2, so we're good now. And we can hit close. Yeah, and then you get the list of all the controller reactions. You can double check them. Okay, now so we want to add the controller parameters. You hit the add controller parameters button, and then it'll give you this another user interface. It's just same thing as the plant reactions and plant parameters. So what are the parameters? The controller parameters are mu and theta and eta and k and delta, and there's kappa 1, and finally there's gamma underscore c, the dilution rate. Okay, now we're done. One more thing, we need to specify the propensities of each reaction. So once you hit the edit controller propensities, it'll start listing the reactions that you already entered. So in this case, this is the constitutive production. The rate is just mu. This is the sensing reaction where the propensity is theta times x2. And the sequestration is eta times Z1 times Z2. The positive actuation, that's just K times Z1. And the negative actuation, that's delta times X2 times X1 divided by X1 plus kappa 1. Okay, so there's the dilution reactions, that's gamma underscore C times Z1 and gamma underscore C times Z2, and we're done. This is gonna update the table. Okay, so now we have everything we want. Next step is to update the species and parameters. So this is going to give you the initial conditions table here, which you can change. Let's by just clicking and editing. But now let's keep them with 0, so 0 initial conditions. And these are the initial values of the parameters. You can change them with the knobs later on. So I'm just going to leave them as is, but just let's make the dilution 0 just because. Then you click the save values. Okay, so what do we want to call the network? Let's call it the antithetic PI controller with degradation inhibition. Well, we can't use spaces, so degradation underscore degradation, and the plant here is gene expression. And this also allows you to add an image. So basically, if you have an image like we have here, you can add it. You don't have to. You can always look at just the tables. But if you want to make it more visually appealing, you can draw it using some external software and just add it here. So in my case, I have this already. So let me just go ahead and add it. But before I do that, I would like to create a folder for this new network that I'm creating. So you just go into network types and create a new folder. And again, let's call it the antithetic PI with the degradation. And the plant is gene expression. Okay, so I have an image for that, it's here. Let me just copy it. It's .svg. I'm just gonna put it here. So now I created a folder. This folder is for my new network that I'm just creating. So now I can go ahead and load an image. So once you hit the load image button, you're gonna get this. So you can just go ahead and select that image. Okay, so it'll show you the path here. And finally, you click the Save Network. When you do that, again, it'll give you this, and which asks you to specify where you want to put the created network, the files. So we created this folder for this. So we're just going to use it again. Okay, once you do that, it automatically adds 3 more files. There's the propensity function file, the stoichiometry matrix file, and the configuration file. This is all you need for the app to identify this network. So now you can go back to the original app, which is this. So now I want to add an existing network because we already created one. So once you click this button, it'll give you, the network types you need to specify. So you need to use the configuration file, .mat. Once you do that, this new network will be added to the drop-down menu, which is antithetic PI with degradation on a gene expression. So once you hit that, it will update the plant and the controller and the list of controller species, plant species, and the output. You can also look at the network diagram as well. And you can tweak things the way you like. So for example, now if you hit run, you get this thing here, and we know for a fact that there's an integrator here. I'm using a gamma sub c is 0 here, so no dilution. So the set point is defined as mu over theta, which is 1. And you see that in fact, the output settles down to 1. You can test this with a disturbance panel, but let's do that a bit later. So let me just do the stochastic simulation first. So let me increase the time samples, and let me ask for 1,000, or let's start with 100 trajectories. And then we can hit the run. So you can use the parallel computing toolbox for this, but let's not just use it for now. So this is showing you a bunch of trajectories for the output. It's not going to be very clear because there's a bunch of them. But you can hit the statistics button, which is going to show you the mean in black and the variance in red. And if you want to see all the internal states for x1, x2, z1, and z2 in the deterministic setting, you can just hit the detailed plots button. That's going to generate this figure here, which shows you x1, x2, z1, z2, all of them in the deterministic setting. And the stochastic setting, same thing goes with it. If you're going to see the statistics as well plotted, you can just hit the check mark here and then hit the detailed plots button, and it's going to give you this figure here. This figure is showing you the trajectories for x1, x2, z1, z2, the expectation or the mean for each of them, and the variance, and the final distribution. All of these are based on the 100 trajectories that you run. All right, and there's also one more button, which is export. So you can export all these variables to the workspace. So for example, in the deterministic setting, if you hit export, it's going to give you this list and ask you what you wanted to export, the time variable x1, x2, z1, z2. If you hit OK, and then you go back to the workspace, you will see that those variables are in there, so you can do more analysis, or you can do another plots another type of dot plots if you're interested. Same thing goes for the stochastic setting as well. Okay, so finally, I just want to point out that there's this disturbance panel and tracking panel that you can use. It's off now. You can turn it on, and what this does is that you can specify at T1, which is, for example, pick at T150. What I want to do is I want to, let's say, multiply the degradation of gamma 2 by 2. Let's see. And then when you hit run, you'll see that at time t2, the degradation is multiplied by 2, and then there's a transient behavior, but thanks to the integrator, it settles back to the set point, which is 1, and thus showing through the simulation that, in fact, robust perfect adaptation is achieved and the integrator is doing its job. Now, of course, if you add some dilution, this is not going to be exact anymore. There will be some steady state error. So this panel allows you to do that for 2 times, T1 and T2, and you can use multiple parameters. You can pick controller parameters. So for example, you can do tracking instead of disturbance rejection by changing mu. So if you change mu, for example, at time t equal 50 and multiply it by 2, the set point should be doubled, and that's what you see here. But of course, because there's dilution, it's not going to be exact. There's going to be a small steady state error. But if it's 0, then you get tracking. Basically, you're changing the set point. You can do the same thing here in the stochastic setting as well. So if you hit run, yeah. So I chose here the parallel computing toolbox. So it's going to take a while to run activate the parallel toolbox in MATLAB, but once you do it once you activate it, it will be much faster than without running the parallel toolbox. So it took 16 seconds with the activation, but if you run it again, it's just going to take like quarter of a second. This is how you look at the statistics, and basically that's it. So this app, what I showed you today in this video is a MATLAB application that allows you to build a biomolecular controller to control some network or some plant, and then once you build this network, you can tune things and test for disturbance rejection and tracking, and you look at the deterministic setting and the stochastic setting. You can also export it to the workspace if you want to do further analysis on the simulation, or even use the data, the simulation data that you get for plots for a presentation or a publication.